Hello, dear colleagues. Hello, everybody. My name is Sergey Robatko. I'm from the Admiral Makarov National University of Shipbuilding, based in Mykolaiv, Ukraine. Today, I will present you a topic at the computerized monitoring system with cloud processing of the hovercraft GPS signals. So, GPS signals. My presentation will cover the following areas. The motivation behind this research is the current state of the art, the objectives we set up, the achieve, the main results of work, the future development we envision, finally our conclusions. So the hovercraft are unique transportation vehicle because they move without direct contact with the surface. However, they require significantly more power than traditional cars or the vessels due to the need to create and maintain an air fusion. Accurate GPS data is essential for hovercraft to ensure precise navigation, safety, and operational efficiency. As hovercraft generate more data, especially with the modern sensor and the equipment, managing and processing this data is a real time become crucial. The traditional data processing system may not handle the growing volumes efficiently. Therefore, we need cloud technologies that can manage large amounts of the data quickly and efficiently. There are several main challenges in current hovercraft technology. First, improving the accuracy of hovercraft positioning using the GPS and other technologies is essential. The second, developing GPS integration hovercraft systems for applications like mine detection can enhance safety in a hazardous environment. Third, in implementation that reckoning control methods in important for situation when GPS signal are unavailable, ensuring reliable navigation. Lastly, creating autonomous hovercraft with the integrated GPS and inertial measurement units, UMUS, enhance operational precision during the various tasks. These challenges highlight the need for advanced solution in hovercraft navigation and control system, particularly in the processing and management of the sensor data. The main goal of our research is to develop computerized monitoring system for hovercraft that use the cloud-based processing of GPS and other sensors data. This system aims to improve navigation accuracy, enhance operational efficiency, and increase the safety of hovercraft operations. We plan to achieve this by utilizing modern technologies for real-time data collection and processing, leveraging the power of cloud computing to handle large volumes of the data from various sensors efficiently. The hovercraft is a full length of the 3,000 millimeters and width of the 1,050 millimeters. These designs provides both stability and maneuverability on different surfaces. In operation on a 48 volts lithium iron phosphate battery, known for its highly efficient and safety. The lift system consists of 6 electric fans, 3 of each side, which control the air pressure to maintain height and stability. For propulsion, there are 2 rear and 2 front rotational ring nozzles with the propellers driven by brushless motor, allowing for precise movement and excellent maneuverability. An automated control system manages propulsion, steering, and lift using data from various sensors to make real adjustments for optimal performance. This configuration ensures that the hovercraft operates efficiently across various terrains. So our hovercraft used the Pixhawk 6C controller combined with the Starlink satellite telemetry to enhance its capabilities. The Pixhawk 6C managed the speed and direction of the propulsion system for accurate movement. It controls the steering mechanism, allowing the hovercraft to make precise turns and maneuvers. The controller processes data from the various sensors, including the GPS, gyroscopes, and other instruments, to maintain stability and respond to environmental changes. With the Starlink satellites internet, we achieve real-time communication between the hovercraft and the control center. Operators can control the hovercraft remotely from the variously any location thanks to reliability connectivity. Additionally, sensor data is sent to the cloud for advanced analysis including machine learning applications. So in this schema, you can see basic connection between our models, how it's connecting the GPS, the Pixhawk, between the Raspberry Pi board, the UAV sensor data that is collecting, and the internet supply using the Starlink and the GPS or LTE connection. And here, as you can see, the schema where we collecting the GPS data, ultrasonic sensors data, pressure sensors, gyroscopes by the Raspberry Pi, and then simultaneously sending it to the cloud. We're using the Hessner cloud here. Um, for, for the data collection and analysis, we employ the Raspberry Pi 4B computer. It gathers information from the ultrasonic sensor that measure distance to obstacles, which is crucial for collecting avoidance. Pressure sensor monitor the air fusion pressure to maintain lift and stability. Gyroscopes provide the data about hovercraft orientation and velocity, essential for balance. GPS offers the real-time positioning data for accurate navigation. The Raspberry Pi 4B process this sensor data and using Starlink ensure reliable communication for the data. Looking ahead, there are several key areas for the future development. In terms of hardware improvements, we plan to upgrade to advanced internal measurements units for better stability and maneuverability, especially in the challenging conditions, integrating environmental sensors like temperature, humidity, and wind speed sensor will allow for dynamic adjustments during operations. We are exploring the advanced battery technologies such as solid-state batteries or supercapacitors to enhance operational range and endurance. For the software enhancement, we aim to develop advanced navigation algorithms, including the machine learning for adaptive path planning and swarm intelligence to allow multiple hovercraft to operate together efficiently. Implementation edge computing capabilities will enable a local data processing, reducing latency and dependence on cloud infrastructure. Refining machine learning models will improve prediction accuracy and system diagnosis. Regarding user interface and control system, we can create the augmented reality control interface to enhance situational awareness and decision making for operators. Improving remote control system with the haptic feedback or uh, gesture-based control will allow for more precise operations. Finally, adopting a modular design approach will allow for easily swapping or upgrading of components, enhancing adaptivity for different missions and reducing maintenance costs. In conclusion, we have introduced a novel approach to hovercraft navigation and control by integrating advanced digital technologies, wireless communication, and cloud computing. By utilizing the Pixhouse 6C controller by the Raspberry Pi 4B, our system efficiently manages propulsion, steering, and data collecting, allowing precise operation across various terrains. Real-time sensor data transmission to the Hesner cloud via 3G GSM and Starlink satellites internet enables continuous monitoring and data analysis, including machine learning facilities, informed decision making, and predictive maintenance. This approach adapts to increasing data volumes and the evolving needs to autonomous hovercraft operation. Overall, the integration of advanced hardware and cloud processing enhance hovercraft efficiently and safety. Our research paves the way for the future development, including additional sensors and refined machine learning models, shaping the next generation of autonomous system across the various industries. Thank you, and I'm ready for your questions.
Thank you very much for your report. Any questions, please? Okay. That's some of your results can be used for drones, for example.
Yeah, actually, the PixHawk actually it's a universal platform that is using as the for drones, as the for the some hovercraft or some planes, etc., etc. So this is the common platform that can be used for anything. The difference is only uh, in the platform that you using. So this is the hovercraft, drone, or another one, and the different sensors that is used. So yes, this is the universal thing that can be used in any way.
Oh, thank you. Do you think about how to use these results for a swarm of autonomous hovercrafts?
Actually, it's just a future development, but one of our another PhD students there is we are talking about he's currently investigating the swarms and he's creating the algorithm of these swarms. So this is like the future development, but we already see the possibilities in this area. So how to use it there together, movement in the swarm, etc., etc. So yes, we are on that way to use that one. But currently, we need to use to configure one, and then the two, three, etc., etc., and then
Mhm.
use the swarm technology there, swarm approach.
Mhm. Thank you very much for your very interesting report.
Thank you
Thank
too.
you.
Yeah.